All right, let's run a second problem, another problem here from section 4.4, a little variation from the thing we had before. It's going to just a slight change from what we have worked previously. And that is, this problem is such that I'm going to go ahead and put it up on my iPad and recognize that we've got a cubic again, a cubic function. This is from section 4.4. And the instructions are determine any local extrema, determine where it's concave up and concave down, and C, find any points of inflection. So let's check out, notice that finding local extrema, first derivative test finds local extrema, but the second derivative test does too. And since we're only finding concave up and concave down, we don't have to do the first derivative test. So all we need to use is the second derivative test to get the questions that we need to work with. So we do need a critical point. So I do need to take first derivative and set it equal to 0, but at the same time, I don't need to use the first derivative test. So let's get started. I'm going to first take the first derivative of the function and get 6x squared minus 12x plus 6. And like I said before on a previous time, you can drop down and get the second derivative right now, but while we're right here, let's go ahead and factor this out and see what we get. I see 6 is common, therefore I get this. Okay, and this factors down to x and x, 1 and 1, and they both got to be minus, so therefore this turns out to be a perfect square. So there's only one place that is the first derivative is equal to 0, the critical one. So that means that when I set this equal to 0, the only factor I'm concerned about is x minus 1. That's the only number that can make this thing equal to 0. So that's happening at x equals 1. So there's only one extrema. All right, so there's only one possible extrema. So we need to check that. So let's take a look at what is that when we plug that the critical point, that's our critical point, plug it into the second derivative and see what outcome we get. So I'm going to drop down now and go to the second derivative. First derivative is right here. Second derivative, I take the derivative of that, I get 12x minus 12, which is equal to 12 times x minus 1. All right, and the second derivative test now is if I plug in any critical point and find out if it's positive or negative, I'll determine whether it's concave up or concave down. So if I set x minus, again, x minus 1 is the only factor, so I've got x equals 1. So when x equals 1, so the situation is that I found the critical point and plug it into the second derivative. That's what I want to do. The second derivative, I find that x equals 1. There's the second derivative. So take a look at this. What happens? If I plug 1 in, I get 12 minus 12, which is 0. So the second derivative at 1, the critical point, gives me 0. So what we were looking for is if I got a positive, it would be concave up, and if it was negative, it was concave down. Well, I don't get that. So it looks like there is no local extrema. There's no local extrema. And the circumstance is then, I need to check to the right and check to the left, because if this is a possible inflection point, this is where the second derivative is equal to 0. So that means it's possible inflection point, but I got to check to the left and to the right. So if I have my only critical values at 1, at x equals 1, and if I check at 0 and I check at 2, and plug those into the second derivative, I will determine if the signs change, then that's indicating that it is a point of inflection. That means if it's concave, goes to concave down, concave up, or concave up to concave down, it'll be a point of inflection. So if I plug in 0, I get 12 times 0 minus 12 equals 0 minus 12 equals negative 12. So that's negative. So it is negative to the left-hand side. Here's the critical point. And the second derivative at 2 notice it's going to be positive. So that means on this side it's positive. So that means it's going from concave down to concave up, and that indicates that here it verifies that it is a point of inflection. So the answers to the questions are, since the only critical point was at 1, and that turns out to be a point of inflection, there is no local extrema. So that means there is no local max or local min. And B, the intervals where it's concave down, you can see on the graph here, the far right is 1. That means the far left must be -1. So concave down at the interval -infinity to 1, and concave up at 1 to positive infinity. It's concave up to the right. And C, find any points of inflection. Point of inflection at x equals 1. Now let's verify what the value of that function is. We go back to the original function to find out what it is. So we end up getting 2 minus 6 plus 6 minus 3. Those 6's cancel. We end up with -1. So we've got 1 minus 1. So point of inflection at 1 minus 1. All right? So no local extrema. That means there's no local max, no local min. B, it's concave down from -infinity to 1, concave up from 1 to infinity. And C, point of inflection is at 1, -1. All right, let's go on. That is solving another problem from section 4.4.